So we've mentioned access control previously, and this depends on who can access the object and the actions that the operations they may perform. And as I mentioned before, there is a set of different types of access control: discretionary, mandatory, role-based, rule-based, and attribute-based access control. So discretionary access control is where each object has an owner who can grant access to other users. So Linux and Windows file system use this along with role-based access control. Role-based access control is where access is granted by administrators to groups of users based on their roles. So you may be in the administrator role, for example, and you may be granted access to that to be given special privileges, or you may be in a role that is related to your business function, like accounting or finance or programming. In Linux, operations are read, write, and execute, and are set on each file and directory. In this example here of a file.sh, we can see the permissions that have been set on this file. So the file is owned by the user RIN, and there's special access also given to the group web. It's not necessarily the case that RIN is part of that group, but it would be normal for the user to be part of that group. But you might want to give groups different access to than users. So in Linux, and Macs for example, the permissions are set in 3 groups. So the permissions for users, for the group, and for everybody else. So the user RIN has read, write, and execute access, and the the group web has read access but nothing else, and everybody else outside of those groups or user has read access as well. So in rules-based access control, access is granted based on rules and policies. So devices called firewalls use this type of access control. So firewalls essentially regulate what network traffic can come into a device or go out from a device or from a network. And essentially a set of rules determine what which packets, which bits of network traffic can actually go outward and come in. Cloud service object storage is another example that uses policies that are rule-based to grant access, and that's essentially an equivalent of file storage on cloud services. Attribute-based access control is access granted on the basis of attributes, so the device, location, time of day. So networks such as Wi-Fi may restrict access based on a MAC address or the time of day. So at home, for example, you might have a router that essentially only allows the devices that you've registered with it to access the network, and that's another sort of security mechanism. You can also say things like allow access from mobile devices but nothing else. And then finally, mandatory access control is access granted on the basis of labels assigned to the user and the object. And this is used in situations where access is determined by security level. So for example, if you grant access to a file to only people who are categorized as having access to top secret information, then that's a good example of mandatory access control. Wi-Fi and fixed networks both run TCP/IP, which is a layered protocol. And in these protocols, each layer adds information to a packet of information in order for it to travel over the particular medium, whether that's a cable or wireless. And you can see here an example of where we have host A communicating with host B. We have an application which then wants to communicate over the network, And so it uses TCP/IP. It gets passed down to a layer which is called the transport layer, which then gets passed down to another layer called the internet layer, which then gets passed down to the final layer, the link layer, that controls the sending of data across the network. At the other receiving end, the host B, it goes back up through the layers through link, internet, transport, before finally being handed over to the application. So this will have both hosts will have a network card that is responsible for actually doing the physical communication. So essentially that has to actually know how to transmit data on a physical medium, such as a cable. And so that will be a network interface card, or a NIC, that has done that. And to identify these uniquely on a network, we use a MAC address, a media access control address. And so essentially that's responsible for various hosts being able to identify where a communication is from and where it's going to. So applications don't use MAC addresses to find hosts, they use IP addresses. And this is part of, in the internet layer of the TCP/IP, which identifies the machine that is sending and the machine that is going to receive a packet of data. So the IP address is normally 4 numbers separated by full stops. And so here's an example of a IP address in the School of Computer Science, which is 130.95.1.119. And you can actually always find out what your IP address is for a computer. A number of different ways. You can go to a web page and say, what is my IP address? And it will tell you. Although you've got to be a little bit careful there, because if you're at home, that may be the address that is given to your wireless router, not necessarily your computer. But we'll talk about that in a bit. To make it easier to find these addresses, we don't use the numbers. We use essentially a domain name. So, for example, www.uwa.edu.au translates to the IP address 13.70.147.206. So TCP/IP uses a service called a domain name server, DNS, as a directory to do the translation between domain names and IP addresses. So the DNS is a service that internet service providers and other organizations run to manage their own domain names. And finally, what we're talking about here is an addressing scheme called IP version 4. There is actually a newer version called IP version 6, which uses a longer address format that I'm not going to go into, but we're going to just deal with IP version 4. The problem with IPv4 was that we ran out of addresses officially some time ago, and there was a belief that we needed a new protocol, new addressing scheme, IPv6, which has many, many more addresses that it can allocate. And we should be transitioning from IPv4 to IPv6, but actually we found a lot of different workarounds, like, for example, network address translation, that allows us to continue a bit longer with IPv4. I'm not sure what the reluctance is for countries to be moving to IPv6, but certainly as more and more devices become internet connected, we're going to be forced to actually make the move to the new addressing scheme. So an IP address that we just saw, the 4 numbers, is actually a combination of a network address and a host address. So when you communicate with a computer, you actually sometimes communicate with a computer that is on your same network, or a subnetwork as it's called, without having to go through a router. But quite often you need to access a server or a computer that's on a different network. So for example, if you're accessing a website, that's not going to be on your local network, and you will have to go through routers that connect subnetworks to other networks, and that will have to find the destination network, deliver your message, your packet of data, and then as the response comes back, it needs to be able to find your computer sitting on a particular network. So everything running in your home, for example, runs on a single subnetwork, and that's connected to the internet via a router and a modem. So the network portion of the address is indicated by a notation that goes as follows. So in this case, we have the same address we were dealing with before, 130.95.1.0, and we put the /24. So the /24 indicates how many bits in that address are going to be the actual network address, and the remainder is the data that is used to refer to the actual computer that we're communicating with, or the host. So in this case, we've got 3 bytes that are used for the network and 1 byte that's used for the host. 1 byte can store up to 255 numbers. So effectively, it means that it can handle 254 hosts on that subnet. Now, if you had a subnetwork that had 260 hosts, you wouldn't be able to use this sort of addressing scheme. You would have to change it. You would have to allocate more space for the hosts and less space for the network. Now, this is sort of important because it allows you to identify networks, and when we're exploring networks, we need to know where our host is located and which subnetwork it may be on, because quite often systems administrators or network administrators will protect computers by sort of allowing them to access other computers on a subnet, but not communicate with other things that are on a protected subnet, for example. So actually sort of knowing about subnetworks is reasonably important. At the application layer, TCP/IP decides what application to give a packet to based on an identifier called a port. And so a port is a number between 0 and 65,536, and so it's allocated to applications that are running on a computer that are communicating via a network. So a web server, for example, will be running on port 443, which is essentially the standard port for secure communications over TLS or SSL. And so when we want to find that application, we send an IP packet to the computer that it's running on, which is www.uwa.edu.au, and we also specify the port. So we could actually use this address, which has a colon at the end and 443, but essentially the HTTPS implies that 443 port. So you can put web servers on any port, but 443 is a well-known port, and so essentially that's the default that it's run on. As I mentioned before, a router is a device that handles forwarding of packets to the next destination, so across the subnet from one network to another. And so when a TCP/IP packet goes from network to network, it needs to hop from router to router, and it does that via a routing table. So you can imagine the sort of logistics involved in the internet in terms of getting a packet that you send from Perth all the way over to an application or server that is running in a different country. And it does this by a layered set of routers, all of which have information about the routers they're connected to. It's a little bit more complicated than that, but as the packet arrives, it looks at the destination and it says, I don't know how to get there, but I do know where to forward this packet onto, and it forwards it onto the next hop, and it just keeps going until it gets to the destination. So each router doesn't actually know the full path of how to get to a place, so it just basically decides on a basis of certain algorithms where to send the packet to next. That may be within the same country, or it may be a different country. Firewalls are devices that have a set of rules that essentially allow incoming and outgoing network traffic. And so the rules are based on IP addresses and ports, and we can use firewalls then to protect certain networks and applications by constructing these rules. So we can construct secure zones that partition communications for different sets of users. For example, staff and students can access an intranet site, but outsiders can't. And we can have outsiders accessing the main UWA website. So that's all done with the firewall, and that's sort of illustrated in this diagram where we have the firewall here, we have the server that is running the intranet that users within our network can access, and then we have the main website which users outside the network going via the internet can access directly as well. And we do that through a firewall. So firewalls also exist on computers, and so your Windows machine or your Mac will have a firewall as well. Your router at home that controls your Wi-Fi access will also have a firewall, and essentially it protects the firewall on your computer will protect essentially traffic not being able to come into the computer. It'll just block most traffic that it's not interested in. You can open this up and allow for other traffic to come in, but by default it's set to block anything that you don't really need to have access. Looking at one of the other protocols that's important in networking, we have HTTP, which is the protocol that is used for resources like web pages, images, and media files that are served from a web server. So essentially, when we talk about the World Wide Web, or we talk about the web, and most people think of the internet as essentially as the web, they're really talking about anything that has been enabled by this protocol, HTTP. It operates at an application layer of TCP/IP, and it uses URLs, the addresses that we use, which are actually called uniform resource locators, and that essentially points to a specific resource, whether it's a file, an image, or a media file that you're trying to access. So in the initial implementation of HTTP, it was very simple. We just wanted to have a way of having a file on a server somewhere and being able to fetch that file using a sort of structured addressing scheme, which became the URLs. HTTP is unencrypted and so is not confidential. And so to do that, HTTP is run over a secure protocol, which is TLS. So HTTPS is a secure version of HTTP, hence the S part of it. It initially used a protocol called SSL, Secure Socket Layer, and that got changed into what's called Transport Layer Security, or TLS. Although HTTPS is still referred to as SSL, and we still talk about things like SSL certificates, even though they're nothing to do with SSL anymore, because it's an old and defunct protocol, and we now should really call them TLS certificates, but we don't for some reason. So the current version of TLS is 1.3, although 1.2 is pretty much the dominant format at the moment. TLS makes use of certificates that have verified identity to identify the server, and they can basically, and also the server's public key. We talked about this in the cryptography section, where we can have certificates that are issued by certificate authorities to prove the identity of a server, so that you know when you access your bank, for example, and you get the padlock, and you click on the certificate, that it's been essentially checked and verified by a certificate authority. TLS works by exchanging a series of messages between a client wanting to communicate with a server. And the first thing that it needs to do is agree what cipher is going to be used. There's a whole range of different encryption protocols that the client and server may use. And this is so that if you're dealing with an older client, for example, that may not know some of the newer protocols, the server can still handle that by saying, okay, you're using an older cipher protocol, in which case I can do that. So the client and the server agree which cipher suites it's going to use. The client will also sort of say, okay, we're going to use this key agreement protocol. We talked about Diffie-Hellman before. There are a couple of other versions of that they can use, and they go through a key sharing process. The server replies saying, yep, agree on the protocol. Here's the key sharing messages, and then the server finishes. The client will then check the certificate, generates keys, and then the client finishes off. And by that time, TLS is set up, and essentially then they can start communicating securely over that connection. Another important network protocol and tool that you can use to ensure privacy on a network is what's called a virtual private network. And this is software that allows a computer on one network to create a direct connection over the internet to another network over a secure link. Effectively, what this means is that you'll get an IP address on the network that you've connected to. And so what does this mean? Well, if you run VPN software, what you will do is access that through some VPN service provider that will have a server in a number of different locations in different countries. So when you connect to that server using a VPN, you'll get allocated an IP address from the server or the network that you're connecting to, and essentially that will geolocate you and locate you in that particular country, because they'll use a set of IP addresses that are particular to that country. And so when you communicate over that network, you're effectively then communicating as if your computer was local to that network and could have been in Paris, say, in a house there instead of your house in Perth or wherever. So VPNs can run over a number of different protocols themselves, like IPsec, OpenVPN, and a newer protocol called WireGuard. So again, if you're looking for VPN services, check what protocols they allow. WireGuard is the newest, and that's come along, and most VPN providers will now provide that as well. Communication is encrypted, and so not visible to anyone inspecting traffic, even to the ISP you're using. So once you've connected to your VPN provider, then your ISP, your telecommunications provider, can't actually see what the traffic is. Now, of course, your VPN provider can, and you've got to trust them when they say that they don't look at what you're doing and they don't keep log, for example. So you've always got to be mindful that they could potentially be compromised as well. And so this gives you a certain level of security, not absolute security. As I mentioned before, connecting to a network in a different country will make it appear that your computer is there. This is sufficient to basically satisfy services like Netflix and others, that you're actually in America, for example, if you want to look at American shows on Netflix. And so there are other things that VPN providers do to try and convince Netflix that you are actually watching from America. That's not just restricted to the location that you are. The other thing to bear in mind is that locations can leak through other sources such as your browser. And so if you're doing this from a security perspective, there are other considerations you have to have to make sure that you're protected and not divulging your location. The final point is that VPNs do not provide anonymity. So once you've connected to a service, you're still going to have to do the usual things of having an account, proving who you are, and at that point you do not have anonymity. there are other ways of doing that, and that is where something like Tor and the dark web come in. So this is sort of an interesting system that was essentially funded in the first place by funding from the US Navy, and they were looking at ways of providing their own services with secure communication. And so the Onion Routing project or Tor came about, and that provides IP anonymity, but to a much greater extent than just VPNs do, because it bounces basically packets around a set of Tor services, or Tor servers, that are called relays or nodes. So what the client does, it's not like routing normally, where essentially the client says, here router, here's a packet, send it on to my destination, and the router will then decide where to send it. In this case, Alice's client obtains a list of Tor nodes from a directory server and then decides on a path and passes the packet through. And at each stage, the communication is encrypted by adding encryption on top of encryption at each level. So in the next step, the Tor client decides on a random path, as I mentioned, through the nodes, and with each node, the green links are encrypted, the red links are in the clear. So it gets encrypted by the first server, which then uses the destination link's key to encrypt it, and then passes it on, and then gets to the final destination, and then Bob can reply to that server, but doesn't know where Alice has come, because all of that is hidden by the encryption that has happened over the nodes. So Tor uses addresses called an onion address to connect to services that are offered on a Tor network. These addresses are like URLs, and essentially what's called the dark web is a collection of onion services that are not indexed directly by search engines on the regular web. So the dark web essentially operates within the same network as the regular web. The difference is that you can't go to Google and say, give me the address of this dark web. Well, Google may actually know what the onion service is, but whether that's up to date or not is another matter. So there are other directory servers that operate on the dark web, and because of this anonymity and the semi-hidden nature of onion services, essentially lots of illegal activities have flourished on the dark web, and it's where you get dark markets that sell illegal products, and they're paid for using cryptocurrencies. And so essentially that's one of the negative aspects of the dark web. The dark web and Tor itself was set up to enable things like activists and people who are just concerned about privacy to enable to communicate while preserving their privacy. But as with all things, there is a good bad side and a bad side, and it's fair to say that the majority of the dark web users use is illegal, and the range of activities that go on is essentially enabled by the dark web and also by cryptocurrencies as well.